Now we're going to talk about motors. So all DC motors, basically all motors fall into one of two categories. They're brushed or brushless. This is what's the inside of a motor. This is how they work. So these are the brushes. Electricity goes through one, causing this to spin and causing the motor to spin. That's basically it. That's too much information. These are the standard brush motors. Typically, the pros are they vary by models, generally robust, simple, 2-wire operation, simple basically, and they're low cost. The cons, again, they vary by model, low torque, weight, heat issues, brush wears, and rules require one ESC capable of 100 watts per motor. Different types of motors, all the information you will ever need. So, stuff you should know about these common FRC motors. This is important. So, your CIM, this thing, is big, heavy, they're reliable, but they're heavy. The mini CIM, small, lighter, they may say they're faster, but there's a significant drop in power and torque. The 7075 Pro, it's red. 7075 red line. It's crazy fast, feather light, fan cooled motor with the wattage equal or greater to a CIM. There's lower torque, but it will release out smoke if it stalls for more than a few seconds. But it is slowly becoming mainstream for powering drivetrains before the release of the Rev Neo BLDC. This is called a bag motor. It's about a third slower than this. This is the bag motor. It's about a third slower than the 775 Pro. Has a low wattage rating, but with higher torque and greater tolerance for stalling. This is the RS 77515. It's pre-installed on the AndyMark PG series motors, but they're almost never really used. These are brushed DC motors. These are not robotics, so this is like slow blowers. These are brushed DC motors. They are motors with pre-installed gearboxes for large gear reduction. They're mainly repurposed with the KOP. Higher torque can wire two motors to 1 ESC and some resistance to backdriving. And backdriving is if you round it up this way, gravity and weight and tension doesn't unwound it. PG series motors are very heavy. They're non-standard output shafts on auto/throttle modes, and they tend to be very slow. This is a worm drive. This is more than you know. Motor spins this. Spins the worm, which is that, and the worm gear spins because it's spinning that, and the output is going to cause it to spin. It's resistant backdriving, 90-degree transfer motion, compact gear size, increased torque, but there's a significant reduction in speed. These are servos. So this is a PWM, which we'll get later, control motor with integrated gearboxes for light-duty action. Opening a shutter, flipping a switch, shifting gears. Good rotation control, good torque for size and weight, connect directly to the robot rear. It's limited to 180-degree rotation. Plastic gears can break/wear out if overloaded. This is a hobby servo. This is more to know than anything, but if you feel free to read it, there you go. This is a brushless DC motor, so this is basically telling you how it works. How do they work? Magnets in the middle. Electrical charge causes it to spin. So a brushless DC motor. This is the first ever FRC legal brushless DC, offers mediocre performance at a high price tag, but it's got integrated ESC, so it's fine. Also, BLDC, brushless DC motor. There's no brush wear or arcing, but it's rare. And the Robot Spectre, like, wow, you have one of these. Though it is expensive and slow powered. This is the brushless DC motor by Rev Neo. So This is a brushless DC motor, Rev Neo brushless motor. It's a drop-in CIM replacement that's compact and lightweight with an integrated encoder. It's efficient, lightweight, small, and powerful. Integrated Hall effects and temperature sensors, but the only issue is it only works with spark motor controllers. These are skills of section 8, and I'm pausing the video right there before I get back to you. Okay, welcome back. This is section 9, gears and gearboxes. So there are 5 major gear types. There are spur gears, gear racks, bell gears, and internal gears, and worm drive. The spur gears are most common type of gears. Drivetrain gearboxes typically use many spur gears. Rack opinion, we've seen those. They use rotation to convert linear motion. Bevel, they're 90 degrees angles. They can be mounted as other angles as well. So a little bit, did you know that? You have internal gears where you have the gears around it and just spins it. Their main use of internal gears are for planetary gearboxes, and then you have worm drive. We've seen this before. Feel free to pause the video here. This is a little bit more. Would you like to know? Did you know this? So feel free to pause this video here, read this. They're just telling you important stuff like important. They're just here to tell you important terms and stuff, such as the tooth count, which is number of teeth, diameter pitch, so it's number of teeth per inch of its diameter, and then the bore, which is this right here, it's the size of it. So in gearboxes, there's many different types of gearboxes. You have a single speed gearboxes, only one single speed. And then you have, this is how you do gear ratio calculations. You do B over A, D over C to get your overall gear ratio in your planetary gearboxes. And then there's also a design calculator to see your gear ratios and all of that good information. Again, just tips for this. Then you have a 2-speed gearbox, which can have more than one speed. Issue is the significant cost is complex and they can fail due to wear on pneumatic or mechanical issues, but there's a shift to overall different gear ratios. And then you have planetary gearboxes. They're heavy, expensive, and not modular, but they're powerful, compact, and durable. Parts are replaceable. How they work is that you have a motor spinning this, which spins the shaft, the sun gear, around planet gears, around the ring gear. Like I said, this is like an internal gear, which spins it around, and it spins these planet gears, causing this whole thing to move, causing the ring gear to move. Pause the video if you want to read this. This example of planetary gearbox that works, so like a pencil sharpener, you spin the outside, your pencil acts as a shaft, and then using the rest of the sharpeners, it sharpens these as they spin around. These are modular planetary, so these planetary gearboxes are customizable. As you see, this could be like longer, it has different gear ratios. It's a little shorter, compact. This has 2 of them and can be used to rotate this one. So modular planetary gearboxes are basically, well, you can modify them. Lightest, more compact, wide range of possible configuration accessories, and you can read the cons right there. Multi-stage build made too long to fit or to fail under excessive load. Linear actuators, they're uncommon due to their cost and weight, but it's basically electronic alternative to pneumatic cylinders. Linear motion using cylinders, expensive, heavy, bulky, slow. And that is gearboxes for you. Mechanical power transmission. So this is shaft. It's the primary means of enabling power transmissions for most entries in this section. It's a rotating machine elevator, usually circular or a hexagon in cross section. You know what a shaft is. Alright, now this is direct gearing. It is a gear-to-gear ratio. Gear-to-gear ratio of transfer power, primarily used in higher torque applications such as the arms. It's uncommon drivetrain outside of FTC or VEX. And then you have 25 roller chains. They're used in electric scooters and pocket bikes. This is 25 chain right here. Good strength is lighter than number 35, and you can read the pros and cons right here. Number 35 is this big thing. It's fair, easy, quick, and stronger than 25, but it's heavier and may stretch. It's used in older mini bikes. And then this is sprocket, a tooth-wheel design mesh like here or here, to a tooth-wheel design mesh with the roller chain, parts readily available, allows for different gear ratios. Although heavier than belt pulleys, chains can skip teeth when under extreme pressure, which you don't want. Then you have the synchronized belt. As you can see here in this picture, it's synchronized. Pros are lightweight, reliable, with consistent performance. Cons can be it's difficult to get pulley stretching and tension correct in custom builds. The replacements usually involve disassembling a pulley axis, and then you have the belt pulley, this thing itself. So this is the belt here, this is the belt pulley. Let's see, there's examples here. Lighter sprockets. Here are the pros and cons. Feel free to pause the video and read it anytime you wish. This is the urethane round belt. This just tells you how to do it. So you melt ends with a heat gun, place the more ends together with some force in the clamping jaw, like here. Clamp block down on belt, and then you trim the tabs of squished material off the belt. These are bead chains. You really don't even see these, and no one's actually using this in FRC. It's just really cool to know. And that is section 10, transmissions. Feel free to pause the video or see the review questions or the skills. These are passive and stored energy. So extension springs, they're right here. This is for the extruded claw. They can just extend, basically. Then you have compression springs, then you have compression springs, which compress. They go here to here. And yeah, then you have constant force springs, which, exert a constant force. And they're typically to see how much force, to say lift the elevator or stuff. It's, like I said, frequently used on elevators to reduce the load on the motor. So sometimes you might see these constant force springs. They're also called Vulcan springs. Then sometimes you have surgical tubing. It's an easy, great, super fix. Simple and reliable, but it can lose its elasticity relatively quickly, and the older ones can dry out and become somewhat brittle. And here you can see it in action. Then in control systems, you have the battery. This is a battery. You have the main breaker, so basically it turns the robot back on and off. You push black switch to turn on, red button to turn off. It also stops the flow if there's too much to draw, and it will make sure there's not too much electricity and just break the circuit. This is called a PDP. It's a power distribution panel. It distributes power from the battery to the rest of the robot. Uses breaker to restrict how much power is sent, and it's a general to terminate CAN bus connection. We'll get to that later. This is a snap action circuit. It plugs into the PDP. It uses to limit current to branch circuits. Uses breaker to restrict how much power is sent, and it's available in 10, 20, 30, and 40 amp ratings. This is a PWM motor controller. It receives power from the PDP, but supplies power to the motors. It receives controls via PWM from the motor reel, and controls the speed direction of the motor it supplies with power. So this is PWM. This is basically sending electricity. This is like a more to know thing. If you stick around, it's just basically, this is PWM, pulse width modulation. It sends electricity. It's the more you know. It sends electricity on cycles. So you can see it's different amounts of cycles of electricity. Acts as Morse code and turns to code. This is a CAN motor controller. Receives power from PWP. Supplies power to motors. It's a motor controller, so it supplies power to motors. Designed to be a part of CAN bus network, but you can see PWM from the real as an alternative. Configured to control or controlled by other CAN bus devices, and controls the speed and direction of the motor that supplies power. This is a more note. It's a CAN bus. If you'd like to pause the video, here it is, and here is the second part. This is a CAN bus decoded, so this is basically how it works. This is it, and a more user-friendly version is right here. So basically this tells you what it's doing right now. If you just compare this one and this one, you can basically understand what the CAN bus is. Again, this is a more you know, but here it is. This is a voltage regulator module. DC to DC converter with both boost and buck voltage regulation. Boost converter. It steps up while setting down current. Buck converter steps down voltage while stepping up current. It can go back and forth and used when components require special protected power like routers, light rings, and flashlights. And here is your VRM voltage regulator module. This is a pneumatic control module. It signals solenoid to actuate the cylinders. It controls the pneumatics. Yeah. This is the Open Mesh OM5P-AC dual band 1.17 GB per second access point. It's onboard Wi-Fi. Lets us connect to the robot and control it from nearby computer. Communicate with the robot reel over Ethernet. Connects to VRM for power. Can be used with a power over Ethernet injector and must be configured at the competitions. Needs to be flashed with updates to work with the field management system. Here it is. This is the Robo Reel. This is the brains of the robot, where code is uploaded and ran. Sends signal to the CAN chain and PWM. Has digital, analog, and port for sensors. Has port for signal lights. This is the brain. This is where all the magic happens. The Robo Reel. Now we're talking about wiring. So in this section we're going to learn about tools, equipment, wire cable, terminal, and connectors. Tools. This is the wire stripper. It strips wires. That's pretty much it. You can read this if you want, but I'm not. This is how you strip a wire. You put it in, put it at the right size, and then you pull the wire stripper toward the end. The insulation slides right off. Choose the right size. If it's too big, it won't strip it at all. If it's too small, it's going to make dents in it. And dents are not good. You damage the wire and shortage can occur. Don't put it in the smaller size. Put it in the right size. This is the Wago tool. A flathead screwdriver will work. You put it in here and then you put the wire in the wire terminal. But do not apply too much force because it's easy to break the plastic tabs in there in the rectangular hole. This is basically how you wire PDP. These are cryptors. They crypt your wires. You'll see what I'm talking about if you don't understand. There are many different types, and it's important to use the correct dies or tool gauge along with quality terminals for good results. This is crimping your wire. That's your final product. That's what you need to do. Wire in, you put this thing over the top, and then you put this metal thing in there, and then you use the crimpers right here. Put in the right slot. Squeeze. And when you squeeze, you should crimp the wires like that. Easy. This is a multimeter. Checks the voltage so your robot's not charging like 20 billion volts onto your motors or your robot. Yeah, read this if you want. Pause the video. This is the chassis isolation test. This is check your voltage. You switch to ohms resistance, turn on the battery, touch the metal part because there's electricity here, and reading should be below 3k ohms per the rules. Otherwise, you don't have enough resistance. Pause the video here if you want to read more. These are ferrocrimptors. Sometimes you don't want to use the other ways crimptors. You want to crimp these guys for like this. Same process. These are ferrocrimptors. Read it if you want. Soldering equipment. This is, yeah, it says for itself. This is how you solder. That's the soldering material. And you basically melt soldering material to combine base level circuit boards. Read it.